In this video, I want to talk to you about generative adversarial networks. We encountered the word adversarial last week, and so this is going to be using an adversarial concept in a slightly different way. So the goal is to see a game theoretic approach to generating new input samples. So it's kind of a mix of adversarial attacks and variational autoencoders in terms of functionality. But let's get into the topic here. Okay, so a generative adversarial network, or a GAN, G-A-N, is comprised of two networks that are competing against each other. So here I'm showing on the left here is a generative network. So it takes some sort of random seed input, which we often call Z, and it spits out, hopefully, an image or something. Then the other network is the discriminative network. It takes an image or whatever input, and it outputs a class. So generative is generating images or generating inputs. Discriminative is classifying them. Now, in a GAN, these two they're put together, so they're basically competing against each other. So I've got them in a line here. So I've got G, the generative network, on the left here. So we have the random seed going into the generative network. It's spitting out maybe an image or some other type of input. It's spitting out something that can be taken as input into the discriminative network, which is D over here. Now the job of the discriminative network is to determine whether the input was real or fake. So it's either real or it's fake. So the discriminative network here is a little bit different than the original discriminative I told you about, where it's classifying as airplane or cat or building or whatever. This is only concerned with real or fake. So the discriminative network is not just getting inputs from the generative network, it's also getting inputs from a data set. And those data sets, the data set has the real images and the generator is creating the fake images. And we want the discriminator to distinguish between the two. So the generative network is trying to fool the discriminative network into misclassifying fake or generated inputs as real. Meanwhile, the discriminative network is also trying to learn how to classify inputs as fake or real. So at the beginning, the generative network, before it's trained, is just outputting like noise. So it's not trained, it's outputting garbage. But likewise, the discriminative network hasn't yet learned how to distinguish real images from fake images. So it gets the real training set and it gets the fake noisy images, and that's pretty easy to figure out which one's real, which ones are fake. But as time goes on, the generator learns to, and I'll show you how, the generator gets better at generating things that look like real inputs. It makes it trickier for the discriminator. But by that time, the discriminator has learned better what the distribution of the real inputs looks like, and so it's better prepared to distinguish the reals from the fakes. Okay. So, the discriminator is trying to decide, does the input come from a data set or from the generative network? So here's a graphic I took off of the internet, just to sort of as a picture here. First of all, we have our real data set here, which I'll call R. And we can take X from the set of real images, and then our discriminative network here, which I call D, and it has parameters, let's call them theta. So far, this is the sort of thing we've been learning here. You have your input data set, and you've got this discriminative network, a classifier, and it outputs labels. Now what we're adding here is this other branch that produces alternative inputs. So we can have this Z here taken from some distribution, some random, this is basically, it's like a random seed. It's almost like the random numbers or random seeds or random latent vectors produced in a variational autoencoder. It doesn't really matter though. We take those random numbers and we put them through the generator, G, and it has parameters phi. So it's going to take that random vector and output something that hopefully will look like an actual input. But it's actually a bunch of inputs that are fake, right? Because they were generated. Those fake inputs we also put through the discriminator. So the discriminator's job is to determine which ones are real and which ones are not. So in the output of the discriminator network will be the probability that the input was real. So we want something close to 1 for real and something close to 0 for fake. Okay? So to sort of be a little more descriptive here, the discriminative network is D. It takes inputs X and has parameters theta, and it outputs the probability that X is from the real data set. X is from R. And in this case then our target T equals 1, because we want, if it's from the real data set, we want our output to be 1. The generator network, G, takes Z as input, and it's got parameters phi. It creates an input sample from random noise Z with distribution P sub Z. You just choose P sub Z. It's not really it's not something we have to learn or anything. And it produces an input which we'll call X primed, because it's kind of like an adversarial image, right? So I'm using the same notation as the adversarial attacks that we covered last week. And it's equal to G Z phi, right? It's just the generator network. And it's going to be from, or it's going to be what the fake data set is constituted of. And since it's a fake image, the true target is actually 0. Okay, so this is the setup. So now it's time for a little joke. I always thought it would be funny as a professor if students sometimes say, "Can I ask a stupid question?" And the professor, I think it'd be funny if the professor said, "There are no stupid questions. Duh." Okay. So we've got these two competing networks. Now, we're going to be minimizing the loss, but we can sort of constitute our loss in different ways. So let me write out the two different parts to our loss function, two main parts. So our loss is going to be, we're going to try to minimize our loss with respect to the discriminative network parameters and the generative network parameters. And it's going to be the expected value over the real and fake data sets of the loss between the output from the discriminator network and T. Let me move that down a little bit. So these are the real or fake inputs, because they're taken from both the R and the F set. Now the target equals 1 for X in the real input, or equals 0 if X is from the fake Okay, so we, as the people training the network, we know which inputs were real and which inputs were fake, and we just assign targets of 0 and 1 according to which set they came from. So that's part of the loss, but there's also another part. So that part is going to be for training the discriminative network. So in this case, on this side, we're actually trying to minimize with respect to theta to make the discriminative network better at detecting real versus fake. That's for training the discriminative network. Now, on the other side, we also want to minimize the expected loss. So who's helping out the generative network now? That first term was basically giving all this information to the discriminative network, saying, okay, this one's real, this one's fake. Okay, can you work out your gradients and update your parameters? Who's helping the generative network? The second term is going to be what the generative network is interested in minimizing. So we're going to minimize over different random inputs. We're going to generate a bunch of fake images, feed them through the discriminative network, but we're going to do the adversarial thing where we're going to say these images should be an output of 1. Really, they're fake. They should be they should have an output of 0, a target of 0, but we're going to tell it that they're real. And so push, it's almost like a targeted adversarial attack, giving it the wrong target equals 1, and asking it to minimize the loss for that incorrect target, which is going to push the generative network to, or it's going to inform the generative network of the gradients it needs to lower the loss for that incorrect target. Okay, let me write it down and I'll describe it again. The loss, the expected loss between the output of the discriminator when given a generated input. So that's the discriminator. Give it a generated input. So this is a fake input. Now the loss between the output of the discriminator when it's given fake input, really the real answer is the target should be 0, but we want to generate the gradients to help the generator be better at fooling the discriminator. So we're going to adversarially say the target is 1. So this here is the wrong target for fake inputs. Let me try that again. Wrong target for fake inputs. Okay, so it's like a targeted adversarial attack in that sense. This whole second part, we want to minimize with respect to phi, which are the parameters of the generative network, so that the generative network becomes better at producing fake inputs that would try to yield an output target of 1. So we're trying to minimize all of this, but the first term is only being used to update the parameters of the discriminative network. The second term is being used only to learn the parameters of the generative network. Okay, so in a picture, this is sort of the setup here. We've got this training inputs, this data set of reals. So what we have here is the real inputs here. I'll just say x and t. So in this case, the t is equal to a 1 because it's coming from the real inputs. And they're going through the discriminative network. But we also have these random seeds going through the generative network, and it's producing these fake, you could almost say adversarial inputs, but the targets are 0. So this is us helping the discriminative network to learn the reals to distinguish between the real and the fake. And so we have these parameters theta here. We get our output y, and we're comparing it to our target t, which is 1 for real and 0 for fake. And so we have this loss, L, Y, T. And we are aiming to minimize, with respect to theta, the expected loss over the real and fake data sets of the the loss between, I'll just say y and t. Okay. So in this stage, we train the discriminator D to correctly distinguish real from fake inputs. And so we're updating our parameters theta as theta minus, so gradient descent minus the gradient of our loss with respect to theta. So in this stage, the gradients start at L and they propagate down through the discriminator network, just that far. So gradients propagate down through D only. Okay, that's for training the discriminative network. Now what about training the generative network? So in this case, we don't give any real inputs. We only give it fake inputs, but tell them that they're real and try to lower our loss. Try to make updates to our phi parameters, okay, to lower that loss. So again, inputs are the random seed Z. They go through our generative network, which has parameters phi. We get inputs x primed. But this time, we're going to say t equals 1 because we want to try to fool the discriminative network. We get output y, and we say the target is 1, whoops, because we want to trick it into thinking it's real. And we aim to minimize, with respect to phi, the expected value over the fake inputs of L, Y1. Okay, so this is like an adversarial attack with the target set to 1. This is like a targeted adversarial attack. So what we increment, we're interested in helping the generative network here. So the gradients, the gradients from this loss going to go down through the discriminative network and then make its way into the generative network. So the gradients first go through D, then go down through G. And so once we have propagated the gradients all the way through D and then down through G, we can update using gradient descent as phi becomes phi minus some learning rate, I call it kappa again, but whatever, times the gradient of the loss with respect to phi. Okay, so going through D first and then through G is easy with AutoGrad, right? We do this stuff all the time. When we have multiple layers, it's just like you go through the layer D and then down through G. Just when you do your optimization, you only optimize with respect to the parameters in the generator, not optimizing with respect to the parameters in the discriminative network. Okay, there are lots of examples of generated samples created using generative adversarial networks online, and they are quite amazing. I'm showing that these examples I'm showing here are kind of trite now by modern standards. But if you Google GANs and like faces in particular, it's getting really hard to distinguish for us as people. We're like expert at faces. It's getting harder for us to distinguish real from generated faces. But this is a quick example shown from the Street View house numbers. On the left are real images. And on the right are images generated using the GAN that was trained on those Street View images. So a lot of them look very plausible. And MNIST. So on the left is real digits taken from MNIST, and on the right are digit images, fake images generated from a GAN that was trained on MNIST. So generative adversarial networks are a really cool field right now, producing some amazing fake images that are really hard for us to distinguish. It's also kind of interesting, this notion of pitting multiple networks against each other and optimizing them against each other, this sort of, what's it called, game theoretic approach to learning.